Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This is the first paper in the first semester. This lecture is the 48th lecture in the series. In the last lecture, we have learnt about the H parameters. We have not gone deep into the mathematical aspect of the H parameters, but we have seen what are the various parameters that normally we take for the circuit analysis. I have given you the brief about the various parameters like the Z parameter and Y parameter and H parameter. The H parameter is the hybrid parameter which relates the character of one from the input side and a characteristic feature of one from the output side, and even the current and voltage were mixed in the formulation. That is why the H parameter is a very famous and important parameter. In this lecture, we will see some of the mathematical aspects of the H parameter, and we will try to meet the objective of learning the H parameter, that is, how to draw an equivalent circuit for the transistor. So, before we start today's lecture, let us have the session outline of this lecture. In this session, we are going to see the significance of H parameters, the transistor equivalent circuit, and also the H parameter for common base and common collector modes. First, let us learn the significance of H parameters. In the last lecture, I have introduced the concept of two-port network. The current from the input side and voltage from the input side form two variables, and similarly from the output side, the current and voltage form the other two variables. Two are taken as the dependent variables and two are taken as independent variables. By using the mathematical technique, we could formulate some of the expressions, maybe the ratios, which have much relevance to the terms that we come across in the transistor circuits, like the input impedance, output impedance, voltage gain, current gain, etc. Each parameter differs in the way we take the dependent and independent variables. That concept I have covered elaborately in the previous lecture, and the importance of H parameter also has been seen in the previous lecture. In this lecture, we are going to see the importance of H parameter. Why the H parameters are important? Mainly the significance. Let us see the significance of H parameter and then go ahead with the mathematical aspect of finding or calculating the H parameter. So, let us see the significance of H parameters. The following are the significance of H parameters. They are real numbers up to radio frequencies. They are easy to measure. They can be determined from the transistor static characteristic curves. They are convenient to use in circuit analysis and design. Easily convertible from one configuration to another. Readily supplied by the manufacturers. The important features are highlighted in the slide that we have seen. I would like to highlight two important features. One is the main advantage of using H parameters is the third point which I have shown. They can be determined from the transistor static characteristic curves. We need not do anything else further to find out the H parameters. We have learned how to draw the characteristic curves for transistor, namely the input characteristics and the output characteristics. How do we draw some of the data, some of the information from the characteristic curves? That we have learned elaborately. Actually, if we map the terms that we come across in H parameter are very much correlated to the information we gather from the two characteristic curves. From the input characteristic curves, we could find the input impedance and also the voltage gain. Those two are the two H parameters that we have seen just now, maybe in the previous lecture. Similarly, from the output characteristic curves, we could determine two factors. One is the output impedance, the other one is the current gain. These two are also again the two other H parameters. So, from the characteristic graphs, the H parameters could easily be calculated. The other significant features are also important, but this I wanted to highlight. And one more thing, when we get a transistor from the market, we need to know certain factors about the transistor. Maybe a transistor is identified a number. Those all we have seen when we learnt about the transistor. For example, BC107 is an NPN transistor. When we purchase this transistor from the market, we should know certain features about the transistor. Already they are available, but the manufacturer should provide some information about the transistor, maybe the type of transistor, whether it is NPN, PNP. So, it is an NPN transistor. And then what about the current gain, voltage gain, all the information should be available. If they are provided in the form of H parameter, that has much relevance to the circuit design. So, that is why the H parameters are very important. They are readily available from the manufacturer of the transistor. And other points are also important in the significance that we have come across now. Now, it is time for us to learn how to draw an equivalent circuit for the transistor. With these H parameters, how do we convert a transistor into an equivalent circuit? So, we are interested in that aspect only. The H parameters are very much helpful in replacing the transistor with the parameters that replacing the transistor with the parameters that we have just now learnt. So, let us see how we can draw an equivalent circuit for a transistor. The equivalent circuit of a transistor can be drawn using simple approximation, but by retaining its essential features. These equivalent circuits will aid in analyzing transistor circuits easily and rapidly. I would like to recollect the two-port network. V1 and I1 are the input variables, V2 and I2 are the output variables. So, a transistor should also have this feature intact when we draw an equivalent circuit. Right now, we have 4 H parameters with us. One is the input impedance, the other one is output impedance, and then the current gain and voltage gain. Maybe if not in the direct form, the gain, if it is not taken directly, at least the inverse of the gain, the forward gain and reverse gain, like that we have 4 parameters. Now, the 2-port network just now we have seen 2 inputs and 2 outputs, and how it has got relevance to the transistor, that also we will now see, and then go ahead with the equivalent circuit for the transistor. Now, let us see a typical transistor and correlate the 2 input variables and 2 output variables that we have considered. Let us have a look at the transistor circuit now. This is the transistor circuit. So, here IB is equivalent to the I1 that we have seen in the 2-port network. Similarly, VB is equivalent to the V1. Here the VC is equivalent to V2 and IC is equivalent to I2. Let us quickly see the variables we have taken in a 2-port. This is how we have taken, and their equivalents in the case of a transistor also now we have seen. Using the 4 H parameters, how we could draw an equivalent circuit for a transistor. It is time for us to learn about it. Now, let us have a look at the H parameter equations and try to see how we could replace a typical transistor with an equivalent circuit which contains the 4 parameters just now we have learnt. To derive the hybrid model for transistor, consider the CE circuit shown in the figure. The variables are IB, IC, then VBE and VCE. Just for simplicity's sake, we are taking them as VB and VC. The VBE and VCE are taken as just VB and VC because it is a common collector circuit, it's known. So, we are dropping the second suffix, that is E. So, IB, VE are considered as independent variables. So, this is how we have formulated the H parameter, making a Taylor series expansion around the quotient point IB, VCE, and neglecting higher order terms. The following 2 equations are obtained. This is how we expand the expression when we have the IB and VC as the independent variables and VB and IC as dependent variables. So, we have just done the mathematical treatment to the function. Here partial derivatives are taken and the delta is nothing but a full derivative. Instead of using dVB or dIB like that, we have just taken delta, representing that it is a variation that is possible in the term, in the particular value. So, we are using them, but it has the same meaning as the full derivative. Now, when we further go ahead with the simplification, the equations we obtain are the partial derivatives are taken keeping the collector voltage or base current constant as indicated by the subscript attached to the derivative. So, the delta VB, delta VC, delta IC and delta IB represent the small signal or incremental variation for the base and collector voltages and currents. They are represented by the symbols VB, VC, IB and IC. Finally, we get an expression involving the H parameters. When we use this mathematical treatment and finally write the expressions for the dependent variables which we have taken here, we get the various H parameters. Partly without giving the mathematical treatment, we have got the same expressions in the previous lecture also. Maybe the suffixes are different in the previous lecture, but now they have much relevance to the transistor circuit. So, let us have a look at the equations, and this is the final expression we get for the 2 independent variables VB and IC. and automatically we come across the H parameters appearing here. And here, what is HIE? This HIE is this derivative. Finally, we arrive at the VB divided by IB, which is nothing but the impedance on the input side. The B here refers to the base emitter side. So, the constant Vc. Here, this Vc is to be taken as a suffix, which is telling it is maintained constant. Similarly, here also, IRE is the voltage gain, but taken in the reverse manner. Why I am telling reverse manner? When we say it is gain, it is output divided by input. But here we have taken that as the input voltage divided by the output voltage. So, we will call that as the reverse voltage gain. And this expression finally is simplified as the current gain, output current, which is IC divided by IB. So, it is called forward current gain, and this is the output impedance, which is the IC divided by Vc, but it is not directly taken as the impedance, it is the admittance, because the inverse of the impedance we are getting here. So, this HOE is called the output admittance, because it is taken in the inverse form of the impedance. Now, these 4 H parameters are called by specific names, which I have mentioned. So, let us see them all together. What are the names by which these H parameters are called? The HIE is equivalent to the H11 term, which we used in the previous lecture, is called the short circuit input impedance, and HRE is equivalent to the H12, which is called the open circuit reverse voltage transfer ratio, or it is called reverse voltage gain also, and HFE is equivalent to H21, the short circuit forward current transfer ratio or forward current gain, and HOE is equivalent to H22, which we saw in the previous lecture. It is called the open circuit output admittance. Why do we call them as open circuit output admittance? Similarly, the first H parameter is called short circuit H parameter, short circuit input impedance. It is because of the condition that we maintain. When we say it is a short circuit impedance, input impedance, something is shorted, something is connected together. What is connected together? The side is connected together, and we measure the impedance. And similarly, the last one is open circuited output admittance. That means there is a disconnection, something is open, something is not connected. So, it is called open circuited. It is because of the conditions that we impose when we measure the variations. So, with these 4 parameters, H parameters, how do we simplify a transistor into a equivalent circuit? Now, let us recall the 2 equations that we have involving the two equations involving the 4 H parameters. Here, the first equation is VB, which is HIE multiplied with IB plus HRE multiplied with VC. This first equation appears as a sum of voltage terms. With VB at the port, the right hand terms HIE is a resistance which has potential drop of HIE IB, and HRE is a controlled voltage generator whose output is dependent on the voltage at the output port. So, what do we infer from the first equation? The first equation is nothing but a voltage equation. The VB is equal to 2 terms we have, one having a parameter H parameter, another having another H parameter. The first H parameter has a potential drop of HIE multiplied with IC. The second equation has a voltage ratio form, it is HRE multiplied with VB. So, how do we interpret them? It is nothing but the summation of voltage. So this is vital for us for drawing an equivalent circuit. This we will keep in mind. Now we will get the interpretation for the second equation, which has the current on the left hand side. This is the equation. IC is equal to HFE IB plus HOE VC. The second equation states the sum of currents. The current IC enters at the output port and HOE VC leaves through the resistance, which is 1 divided by HOE. HOE is the output admittance, so we take it as the inverse term here to mean the resistance. The other term HFEIB is leaving current due to the controlled current generator. So second equation is the current equation. Summation of two currents results in a current, which is the current drawn from the circuit. So we have one equation with the voltage, another equation with current. How do we use them for replacing a transistor with an equivalent circuit? These two equations have tremendous significance in simplifying a transistor into the equivalent circuit that we have been long waiting to have a look at the equivalent circuit. Now let's have a equivalent circuit of the transistor, and this is the long awaited equivalent circuit. Only for drawing this equivalent circuit we have even learned all the H parameters. Now I would like to explain the circuit elaborately. The first equation involving the voltage. So this is having the voltage part VB, which is equivalent to VI here. This is the IB represented as I1 here. So the V1 is the product of these two and the product of these two with the summation. So it has the potential drop of H11, this is the input resistance and this is the current that is flowing, and another term which is the voltage generator. The voltage generator is represented by this symbol in electrical circuits. So it is H12 V2. So the first equation takes care of this part, which is the voltage term, and surprisingly when we have a look at the output side, the second equation is highlighted. It is a current equation. We had IC, which is shown here as I2, and which is equal to one current generator. What is the current generator? It is I1 multiplied with H21. H21 is the forward current gain. So this is the current generator, and this is again the current term H22 V2. If you multiply this, H22 is the admittance. Admittance multiplied with voltage will give us the current. So that is how these two supply current to the output current, that is marked here as I2, which is equal to IC, or the collector current. So we have clearly seen the two equations that we had for understanding the H parameter have very much, they are very significant for drawing the equivalent circuit for transistor. The first equation takes care of the input side in terms of voltage, and the second equation takes care of the output side in terms of current. That's why it's called hybrid parameter. In hybrid, the current and voltage are intermixed so that we get advantage of drawing a transistor as a very simple equivalent circuit. Hereafter, for all the circuits that we analyze, a transistor will be dealt as a current source and a voltage source, just now we have seen. So let's have a look at the equivalent circuit once again and understand how the equivalent circuit is to be drawn. So this is the circuit. I have correlated each term with the suffixes here to the typical transistor variables like IB, VCE and IC, VB, VCE, and this is VBE. Like that each term could be correlated to the actual transistor parameter terms. And is it possible to develop the transistor parameters for the other modes of operation? Let's quickly have only the circuits, and the H parameter for other modes are also possible. The above equations define H parameters of transistor. In CE configuration, the same theory can be extended to transistors in other configurations like CB and CC mode. And the equivalent circuits I would like to show in the next slide. Transistor parameters for CB and CC modes are also available. So, this gives us the gist of the equivalent circuits for other modes also, including the CE mode. But in CE mode only, the transistor is very often used because it has got much advantage in that mode. Migrating from one mode to another mode is also possible using the H parameter. So, I have concluded the H parameter concepts with this lecture, and we will see the session summary of today's lecture. In this session, we have seen the significance of H parameters and the transistor equivalent circuit, and then the H parameters for CB and CC modes, and how we could migrate from one mode to another using H parameters. Now it's time for us to test our understanding of what we have learned today by answering these questions. Give the significance of different H parameters. Draw the equivalent circuit of transistor in CE mode with the help of H parameter. Draw the equivalent circuit of transistor in CB and CC modes with the help of H parameters. With this, I would like to wind up today's lecture. Thank you for listening.